Welcome to a video on the applications of the total differential. We'll be taking a look at propagated error and relative error. So in the previous video we talked about differential z when z is defined in terms of two variables x and y. So if you're not familiar with the total differential, you may want to take a look at that video first. What we're going to do in this video is take a look at applications of using the total differential. First we're going to talk about propagated error. If measured values of x and y are used to compute another value z, then the difference of the function values, or delta z, is called the propagated error. In order to estimate the propagated error, we can use differential z instead of the true delta z. And relative error is very closely related to this. The ratio of delta z to z, which is approximately equal to differential z divided by z, is called the relative error. And this value will give us a percent of error rather than just a numerical value which we get from the propagated error. So it gives us a better idea of whether the amount of error is acceptable or not. Let's go and take a look at a couple of examples. Here we have a right circular cylinder that has a height of 24 feet and a radius of 8 feet. If the possible error measuring is 3 inches, what is the possible error in volume? So here we have our volume formula. The volume is equal to pi r squared h. Well, before we determine the relative error, if the measurements can be off by as much as 3 inches, we first need to determine the propagated error, which we're going to estimate by using differential v in this case. So let's go ahead and write out our formula for differential v using this formula, and then we'll fill in all the necessary information. Before we do that, we can see that v is defined in terms of two variables because pi is a constant. So differential v is going to be equal to the partial derivative of v with respect to r times differential r plus the partial derivative of v with respect to h times differential h. It's equal to the partial of v with respect to r. That's going to be 2 pi r h times differential r. Remember, measuring r can be off by up to 3 inches. Well, these measurements are in terms of feet. So 3 inches converted to feet would be 3/12 or 1/4 of a foot. So differential r would be plus or minus 0.25 plus the partial derivative of v with respect to h. That's going to give us pi r squared times differential h. And again, the measurement is still off by as much as 3 inches, which would be plus or minus 0.25 feet. Now we have all the information we need. The last step is to substitute r equals 8 and h equals 24. Now, for the sake of time, I've already determined the value of this. Just one word of caution. When we type this into our calculator, of course, we're not going to be able to type in the plus or minus. So what we normally do is just use the positive 0.25. That's going to give us 351.8 cubic feet. And then we'll just put a plus or minus on there. However, remember, the goal was to determine the relative error. This is the propagated error, meaning when we calculate the volume, it could be off by as much as this based upon the error in the measurement. But to get an idea of whether this is acceptable or not, we need to determine the relative error. The relative error would be the ratio of differential v to the true volume. So we'd have plus or minus 351.8 divided by the true volume, if there was no error, would be pi r squared h. So we'd have pi times 8 squared times 24. This will give us a decimal. It's going to be approximately plus or minus 0.073, which means our approximate relative error is going to be plus or minus 7.3%. So if this is not an acceptable level of error, what that means is we're going to have to determine a better way of measuring both the radius and the height of this cylinder. Of course, you can see how this would have implications if you were manufacturing these types of cylinders. Let's go and take a look at one more example of this. Here we have a triangle with two sides of length 5 and 12, and the included angle is pi over 3 radians. Now this isn't necessarily to scale, but if we call this 5 and we call this 12, the included angle would be the angle here. This would be pi over 3 radians. And it says if the possible error in measuring the sides is 1/8 of an inch and 0.1 radians for the angle, approximate the possible error in the area and then determine the possible relative error. Remember the formula to determine the area of a triangle when you have the two sides that include an angle is area equals 1/2 AB times sine C, where the sides A and B form angle C, and this is the information that we do have. So here's our formula. So first we have to determine differential A, that would be the propagated error or the possible error in measuring the area. And then to determine the relative error, we have to take differential A and divide by A. Notice on this one we actually have A defined in terms of 3 variables, so it's going to change our formula for differential A. Let's start with that. Differential A is going to be equal to the partial derivative of A with respect to little a times differential A plus the partial derivative of A with respect to B times differential B, and then lastly the partial derivative of A with respect to C times differential C. Let's go back to our sketch for a moment. Let's go ahead and call this A, let's go ahead and call this B, and we'll call this angle C. Next, the possible error in measuring the sides is 1/8 of an inch. That would be 0.125 inches. So that means differential A is equal to differential B, which is equal to plus or minus 0.125. And then differential C, the error in measuring the angle, is 0.1 radians, so it's plus or minus 0.1. We're going to need all this information once we determine these partial derivatives. Okay, let's go ahead and find differential A. So the partial derivative of A with respect to little a, treating B and C as constants, will be 1/2 B sine C times differential A plus the partial derivative of A with respect to B, treating A and C as constants, that'll be 1/2 A sine C times differential B plus derivative of A with respect to C. Well, derivative of sine C would be cosine C, so we have 1/2 AB cosine C times differential C. So now we just need to do a bunch of substitution to determine this value. So we'll have 1/2 B sine C, that's going to be 12 sine pi over 3. All of this times plus or minus 0.125. 1/2 A sine C is going to be 5 sine pi over 3 times differential B, which is plus or minus 0.25, plus we have 1/2 AB cosine C times differential C. So 5 times 12 times cosine pi over 3 times plus or minus 0.1. And again, to save some time, I've already determined these values. So the possible error in measuring the area came out to approximately 2.4201, and this would be square inches. Okay, let's go ahead and determine the relative error now. So we're going to take differential A and then divide by the true area if there was no error at all. Let's go ahead and do that on the next slide. Remember, the true area would be 1/2 AB sine C. So that's going to give us 1/2 times 5 times 12 times the sine of pi over 3. And again, I've already done this. It's approximately 0.0931. So we'll say it's approximately 0.93%. As you can see, it's pretty valuable to determine the relative error, because if we said the area was going to be off by as much as, I forgot the plus or minus here, approximately 2.4 square inches, that doesn't seem like a big deal, but compared to what the area really should be, 9.3% seems like quite a bit of error for this situation. I hope you found these examples helpful. Thank you for watching.